Hi guys! In this lesson, I will explain the basic structure and working principle of MOSFETs used in switching, boosting, or power balancing tasks in DC to DC converter circuits, motor driver circuits, and many more power electronic circuits. MOSFETs are the most widely used field effect transistors that operate with voltage control. We can examine FETs in two groups, as you can see here. We had a lesson in which I explained JFET before. I'll explain the MOSFET in this trouble. The abbreviation of MOSFET comes from the initials of the metal oxide semiconductor field effect transistor words. You see the shape of a MOSFET transistor on the left and the symbol on the right. MOSFET also has three pins. As in JFET, one of them is gate, the other is drain, and the last is source. Pin names are the same in MOSFET as in JFET. Their order is not always like this. Locations may vary depending on the model. G, D, and S abbreviations are used for these. In the symbol, the pin naming is like this. We can compare the structure of the MOSFET to a faucet, as in all transistors. We can think of the gate pin, where the trigger is made, as the valve of the faucet, and between the drain to source, where the current passes, as the direction in which the water flows in the faucet. When a trigger voltage is applied between gate and source, a current between drain and source is controlled. MOSFETs are produced in two ways, N-channel and P-channel. In the symbol, the outward arrow on the gate pin is N-channel and the inward one is P-channel. If you remember, it was the opposite in JFET. So, what's the difference between them? The working principle of both is the same. The direction of the controlled current in N-channel MOSFET is from drain to source, while the direction of controlled current in P-channel MOSFET is from source to drain. In other words, while the positive or plus pole of the voltage source is connected to the drain pin of the MOSFET in N-channel MOSFET, the positive or plus pole of the voltage source is connected to the source pin of the MOSFET in P-channel MOSFET. Let's compare MOSFET, BJT, and JFET transistors according to the current they can withstand. While currents close to 1 amp and under 1 amp can be controlled with BJT and JFET transistors, much larger currents can be controlled with MOSFET transistors. We can see this by looking at the datasheet of some MOSFET transistors. For example, when we look at the datasheet information of the very widely used IRF-Z44 MOSFET, there is information that current can be controlled up to a maximum current of 49 amps. This current value is really a great value. In addition, a maximum voltage of 55 volts can be controlled with this MOSFET. When we look at the datasheet of IRF-540 MOSFET, another widely used MOSFET, there is information that a maximum current of 23 amps can be controlled and a maximum voltage of 100 volts can be controlled with it. The fact that a wide range and much greater current and voltage control can be achieved with MOSFET increases the attractiveness of MOSFET compared to other transistors. For example, you see a DC to DC boost converter here. The circuit diagram for this is basically the same as here. The amplification process is according to the switching speed of the MOSFET located here. Triggers are made at high frequency values at the kilohertz level. In this way, MOSFET and shock diodes are preferred in order to obtain healthier results instead of using normal silicon diodes in order to respond to high-frequency switching speeds in converter circuits. DC to DC converters and motor drivers using MOSFETs naturally get hot because very high current flows through them. As such, they need coolers. We usually see MOSFETs in circuits as fixed to heat sinks that will dissipate the heat, like you see here. For example, in the motor speed control circuit you see on the right here, there is a heat sink fixed to the MOSFET, which I show with the red arrow. We can see that there are heat sinks connected to MOSFETs in this DC to DC boost converter amplifier converter circuit you see on the left. Well, let's look at the basic working principle of a MOSFET now. Here you see a simple motor speed control circuit with the circuit diagram in the upper left corner. There is a small DC motor connected to the drain pin of the N-channel MOSFET. There is a DC source to drive this motor. Here, there is a potentiometer connected between the gate and source pins of the MOSFET to provide the voltage to trigger the MOSFET. The reason for connecting a resistor between the potentiometer and the MOSFET is that a reverse current in the MOSFETs does not damage the circuit elements connected to the gate pin. Thanks to the resistor here, the intensity of that current is reduced. Thus, the circuit devices connected to the gate pin are not damaged. If we talk about this circuit, since there is no damage to the potentiometer, this circuit will work smoothly even if there is no resistor. Now, when we change the resistance value of the potentiometer here, a voltage will be applied between the gate and source of the MOSFET. With this voltage, the MOSFET will be triggered and the current coming out of the positive or plus pole of our power supply will flow between the drain and source pins of the MOSFET by following the path we have shown with the arrows, and our motor will rotate with this current. As the trigger voltage will change by increasing or decreasing the resistance value of the potentiometer, the drain current will change and the speed of the motor will change according to this current. We can also control the motor by connecting a power supply that provides a constant 5-volt voltage instead of a potentiometer. While the MOSFET is triggered above 5 volts, it is not triggered at the voltage below. For a better understanding of this motor speed control circuit, I built the circuit on a breadboard. With a 9-volt battery, we can control the speed of a small DC motor with a potentiometer thanks to the MOSFET in this way. As here, the working principle of systems with big electric motor fans is the same. With MOSFET, we can control the speed of a motor not only with a potentiometer, but also with a microcontroller, as here. Since the resistance value on the gate pin of the MOSFET transistors is very large, there is no current flow. That is, the trigger part and the part connected to the load are isolated from each other. As such, MOSFET can be easily used with a microcontroller such as Arduino. Thanks to the 5-volt square wave received from the PWM signal output of the Arduino, speed control can be done easily. According to the duty value of this signal, that is, by adjusting the expansion and contraction of the signal, we can make the motor rotate fast or slow. Here, the resistor connected to the source pin of the MOSFET provides protection for the reverse current that may come to the Arduino microcontroller. Since MOSFETs are easily affected by static electricity, and due to the resistor used with it, they are generally used as driver modules, not alone in the circuit. Thanks to these modules, MOSFET connections can be made easily in the circuit. Thus, ease of use is also ensured. For example, microcontroller, motor, and power supply connections can be made easily when the MOSFET is not a standalone MOSFET driver circuit module, as is the case here. When we look inside this module, we see the circuit here. The MOSFET driver circuit module is formed by combining the required resistor and MOSFET connections. Thus, the digital signal input, load connection, and power connection to be connected to the microcontroller are gathered on a module to provide ease of use. This is the basic structure and working principle of MOSFET, which is used in power electronic circuits and many other electrical and electronic circuits, friends. I hope it was helpful and you liked it. Hope to see you in our next lesson. Goodbye!